Good morning, everyone. Today we are pleased to welcome Professor Gordon Ogilvie from University of Cambridge to give us a seminar on celestial fluid mechanics, new perspective on hydrodynamic of astrophysical disks. So Gordon received his PhD from Clare College of University of Cambridge in 1997. After that, he continued his research career as a Damon Baines Research Student Fellow in Clare College. He then became the Royal Society University Research Fellow in the Institute of Astronomy of University of Cambridge in year 2000. He has then moved to the Department of Applied Mathematics and Theoretical Physics of Cambridge since 2005 and became a professor of the department since 2013. So Gordon's research focused on magnetic field and dynamics of astrophysical disks, including protoplanetary disks, accretion disks around binary stars and black holes, and also rings around giant planets. So in today's talks, Gordon will discuss some of his recent research on astrophysical disks and introduce some novel theoretical method for studying them. So now let us welcome Gordon. So Gordon, you have the time. Gordon, please.
Okay, thank you very much, Jason, for the introduction, and thank you also for the invitation to give this seminar. Sorry, I haven't been able to visit Zurich in person on this occasion, but hope to see you on a future occasion. Yes, so this is a strand of research that's been going on for a while and has involved quite a few collaborators over the years, most of whom are listed here. Okay, so to begin with, just a brief introduction to astrophysical disks in general. We're dealing here with material orbiting around a massive central body, a star, a black hole, or maybe a planet. But the material is in the form of a continuous medium, usually a fluid, usually a gas. And there's an interesting interplay in this subject between, on the one hand, orbital dynamics or celestial mechanics, and on the other hand, fluid dynamics, or more generally, continuum mechanics. Astrophysical disks are usually assumed to be circular, coplanar, and also thin. And indeed, they're usually Keplerian, meaning that they're dominated by the gravity of the central object rather than that of the disk itself. So this means that the angular velocity of the circular orbital motion in a standard Keplerian disk is given essentially by Kepler's third law and decreases outwards in this way. So this is an example of a natural shear flow with an angular velocity that decreases outwards. And differential rotation. Now, the classical accretion disk theory is mainly concerned actually with the processes by which accretion disks or astrophysical disks generally evolve and become luminous and visible. And that's really all to do with angular momentum transport. So if there is any process in the disk that acts similarly to a viscosity or a frictional force, then it will transport angular momentum outwards in this shear flow from the more rapidly rotating inner parts towards the less rapidly rotating outer parts. And if angular momentum is removed from the inner parts, then they can spiral slowly inwards towards the central object to be accreted by it. And as mass falls into the gravitational potential well, it liberates energy, making the disk hot and luminous. And indeed, some of the most luminous objects in the universe, such as active galaxies and quasars, are powered by this mechanism. Okay, now I've been interested for quite a while in a more general concept of a Keplerian disk. And we know that around a Newtonian point mass, the orbits can generally be inclined at any angle, or they can be elliptical. And we can consider a Keplerian disk made up of these variably inclined or variably elliptical orbits. And I mean, to the extent that the motion of the material in these thin disks is dominated by gravitational and inertial forces, these orbits can be seen as the first approximations to the streamlines of the gas flow in these disks. Now, having, so it's very important that these orbits are closed and they don't intersect their neighbors. At least that's true if the eccentricity varies sufficiently slowly with the size of the orbit. So then we can imagine these as gas streamlines that are not in conflict with each other. They don't produce any shocks or anything like that. But having set up a disk of this form, it's then appropriate to ask how do, well, not just the mass distribution, but also the shape of the disk. How do they evolve on timescales long compared to that of the orbital motion as a result of the various collective effects in the fluid? So that might include what's called viscosity in accretion disk theory, which is usually really a label for turbulence and turbulent stresses, or possibly wave processes. But actually just the pressure in the disk and its self-gravity they contribute to the communication of, or the evolution of the shape of the disk, as we'll see. Now, in some sense, this can be thought of as the celestial mechanics of a continuous medium, because in celestial mechanics, we're mainly concerned with how basically Keplerian orbits evolve or are perturbed by various other perturbing forces, which might come from, let's say, other planets in a multi-planet system like the solar system, or whatever other forces other than that of the central body act on particles or minor bodies. Now, for these fluid disks, there are various forces that are causing perturbations from the basic orbital motion. And some of those forces are internal to the disk. They arise from the stresses in the fluid, which might just be pressure, but they could also be turbulent stresses or magnetic fields. There can also be external forces due to companion objects and so on. Okay, well, we're actually hosting a workshop next week in Cambridge, or virtual workshop, which is entitled The Dynamics of Distorted Disks. And I mean, these have sometimes been called distorted or deformed, but perhaps we should just think of these as more diverse and think about the diversity of Keplerian disks that are possible in nature. So, I mean, do these actually occur? Certainly, there's a lot of evidence and a lot of theoretical reasoning as well for considering warped and eccentric disks. A disk can be expected to be warped basically whenever there's a misalignment between the original plane of the disk and almost anything else in the system. So a classic problem investigated since the 1970s is where a disk has formed in a certain plane around a black hole, but the spin axis of the black hole is not perpendicular to the disk plane. So, I mean, the original plane of the disk will be dictated by the angular momentum vector of the material that forms the disk, and that may be unrelated to the spin of the black hole at the center. So here we have material orbiting not in the equatorial plane of the black hole, so it'll be subject to gravitomagnetic torques leading to lens-adhering precession, which will vary strongly with the radial size of the orbit, and that tends to cause a twist and a warp in the disk. So a classic problem is to try to work out the steady shape of the disk in this situation. But other sort of misalignments might include if we have an orbital companion, like a binary star, or a planet with an inclined orbit, inclined with respect to the original plane of the disk, then the disk will become non planar as a result. As for eccentric disks, well, again, eccentricity can be induced by an orbital companion. Actually, even if the companion has a circular orbit, well, if the companion has an elliptical orbit, then it's basically through secular forcing of the disk, it will acquire some eccentricity. But even if the companion has a circular orbit, then there can be mean motion resonances that lead to an instability that produces eccentricity in the disk. I'll show examples of that. And from the observational point of view, there's good evidence for eccentric disks in interacting binary stars, such as the cataclysmic variables. Certain planetary rings, the narrow rings around Saturn and Uranus, are eccentric. And then BE stars, which are very massive, rapidly rotating stars, often have precessing eccentric disks around them. And then there are the tidal disruption events where stars are torn apart around black holes in galactic nuclei, producing highly elliptical accretion disks. There are relatively few observations, direct observations of the actual warps or eccentricity, but here are some examples. Maser emission from this active galaxy and a few others has enabled us to trace out the shapes of warp disks in these galactic nuclei. And this is a well-known debris disk around the young star Beta Pictoris, where there's a warp which is thought to be associated with planets in this system. There are more observations of misalignments from which we would deduce that warps are likely to occur. So here's a young binary system. These are the observations from ALMA and HST, and this is the artist's impression of the system. The point is that each of these two young stars has a disk around it, and each disk is measurably misaligned with the plane of the binary orbit. So we should expect each of the disks to be warped at some level, although that can't yet be measured directly. Another type of observation that's been prominent recently is, well, there have been a lot of developments of imaging of disks around young stars. And here's an example of where shadows in the outer parts of the disk have, which move quite rapidly, have been interpreted as being cast by strongly misaligned inner part of the disk that's precessing and casting a moving shadow on the outer part of the disk. So there are several systems like this where strong misalignments have been deduced and associated with warps. Here's a very extreme example of a misalignment where, well, we have a highly eccentric binary star and a disk, well, in the form of a ring, has been found around this eccentric binary, and the disk is basically perpendicular to the plane of the binary orbit. It's in a so-called polar orbit, and there is some nice theory about how the disk finds its way into this polar alignment because of the eccentricity of the binary orbit. As for measurements of eccentricities in disks, they're relatively few, but here's an old example. This is one of these cataclysmic variable interacting binary stars of the superhump category, where during a so-called super outburst, the accretion disk becomes elliptical and starts precessing. And in this case, through the eclipse mapping technique, they were able to map out the elliptical shape of the rim of the disk. Now, more recently, this is an observation of a debris disk around a white dwarf, where some material of planetary origin is being disrupted, producing a debris stream an elliptical disk that's precessing, and there are several systems where this precession has been detected. Okay, now there's been a good amount of work using numerical simulations, much of it using the SPH method. So here, for example, is a simulation using the SPH method of a tilted disk around a binary star or binary system. So the disk is initially tilted at some angle with respect to the plane of the binary orbit. And in this case, it develops a smooth warp connecting the orientation at large distance, and then it lines up with the binary orbit at smaller radius. But what's been found in this type of calculation is that in certain regions of the parameter space, particularly if the disk is sufficiently thin and not so viscous, and if the tilts are large, then there's a tendency for the disk to break into distinct segments. So rather than having a smooth transition, a smooth warp, rather the inner part of the disk breaks off and has only a very tenuous connection with the rest of the disk, and that allows it to precess essentially independently of the rest of the disk. So that's one of the interesting phenomena that's been revealed. Now, these circumbinary disks have also been studied quite a lot in basically a two-dimensional configuration without any tilt involved. And there it's found that they typically become eccentric, even if the central binary, in fact, especially if the central binary is circular. So in this case, eccentricity can develop in the disk as a result of a resonant interaction between the motion of the binary and the motion of the surrounding disk, leading to a growth of eccentricity. And we see this elliptical cavity then, which precesses around, and that causes a whole lot of interesting phenomena, including modulation of the accretion rate onto the system, and can have important consequences for the evolution of the binary orbit. So this is important for both young stellar systems and also binary black holes. Okay, well, related phenomena are also seen in the planet-disk interaction problem. So here is a simulation by Willie and his one of his PhD students some years ago of planet disk. So there's a planet of 5 Jupiter masses on a fixed circular orbit, and it opens a deep gap in the disk. But at least for these parameters, the disk is found to become eccentric through this, through a mean motion resonant interaction, essentially leading to eccentricity, particularly in the disk exterior to the planet's orbit. So that can affect things like the accretion of mass onto the planet, so it affecting its growth. It can affect the migration of the planet, and so on. Yes, we attempted to explain the growth of eccentricity in this type of system through a linear theory, basically explaining how a certain eccentric mode in the disk acquired a positive growth rate through various mean motion resonances. Okay, well, and all this ties in some sense with the super hump phenomenon in those interacting binary systems, where there's a particular mean motion resonance that's thought to cause eccentricity in the disk. And for many years, that was only found in SPH simulations. Grid-based simulations didn't produce any eccentric disks. But well, again, with Willie, a number of years ago, we were able to see this phenomenon occur in a grid-based simulation for the first time. Another interesting recent development has been, well, it involves a combination of warping, or at least tilting, and eccentricity. So this is SPH simulations of disk around a star in a binary system. And here the disk is initially tilted at a large angle with respect to the binary plane. So larger than 40 degrees, we'll see is important. Because after a number of binary orbits, the disk becomes highly elliptical. And this is how the eccentricity varies in time in this type of simulation. So there's a large growth of eccentricity and then damped oscillations, because the disk in this simulation is highly dissipative and it damps out the eccentric mode that results. So this can be understood as a continuous analog for a disk rather than a particle of the Lidov-Kozai process that's quite well known in celestial mechanics, whereby an orbit that's sufficiently inclined by more than about 40 degrees with respect to the orbit of an outer, let's say, binary companion, becomes highly elliptical, and there's an oscillatory exchange between inclination and eccentricity in this system. So we helped to develop some semi-analytic theory of this, in which a disk that's tilted through a sufficiently large angle develops an unstable mode. So this is an initially circular disk. The eccentric modes in the disk become unstable through this Lidov-Kozai process, and growth rates can be obtained depending on the parameters of the disk. There's also a lot of interest in disks around black holes, and again, simulations of this process. In some cases, they produce smooth warps, although here's an interesting example of where, contrary to the classic Bardeen-Petersen effect, the variation of the tilt angle with radius is non-monotonic. We see the beginnings here of an oscillation, which was predicted theoretically. But again, if the tilts are sufficiently large, or the disk is not very thick or viscous, then there's a tendency for the disk to break into independently precessing segments like this. Okay, now some researchers have been able to do this type of simulation with sufficient resolution and with grid-based methods to capture the MHD turbulence in the disk resulting from the magnetorotational instabilities. These are very challenging computations, and perhaps some other things have been compromised to make this possible. Most of the simulations that I showed before are just treating the disk as a viscous laminar flow. Okay, I should also briefly mention tidal disruption events, because at least in some of the simulations of tidal disruptions, where a star encounters the black hole at the center of a galaxy on a highly elliptical or parabolic orbit, what's produced is a highly elliptical accretion disk. Although in some other simulations, depending on the thermal physics involved, there can be a lot of circularization before the accretion occurs. But this is certainly an important situation that we've been investigating to understand the dynamics of the elliptical accretion disks in this type of situation. Okay, well, what can we do in terms of theoretical approaches other than global numerical simulations here? There's quite a long thread of work attempting to derive essentially one-dimensional evolutionary equations describing how these systems behave. One approach is to use linear theory. So you regard the eccentricity or the inclination as small perturbations of a standard circular coplanar disk, and then you can develop some linear theory describing how the eccentricity and inclination evolve, which may involve growth or decay and wave-like propagation. When they're not small, we need a more nonlinear method. And I've been involved in some global asymptotic analyses where we're basically making use of the fact that the disk is thin and that there are separations of length and timescales in the problem to derive evolutionary equations through asymptotic methods. And I'll say a bit about that in a moment. More recently, I've also been trying to use variational methods to derive these equations. I probably won't say a great deal about that here, but it does provide, I think, some useful insight into what is otherwise a rather complicated set of equations. Another approach that I've been developing is to derive some reduced computational models, alternatives to the global numerical simulation. I'm interested in what can be done using local computational models to study the physics of these situations. And I'll also say a bit about an affine model that I developed to reduce the problem basically to a two-dimensional one. Okay, so the global asymptotic methods that I developed, roughly speaking, it goes like this. You assume that you've got either a warped or eccentric disk, which has some geometry that is slowly evolving, and it's based on the geometry of a family of Keplerian orbits. And then we introduce a coordinate system that's adapted to those orbits. It is somewhat complicated because it's a non-orthogonal coordinate system. It's also time-dependent, although only slowly. It evolves on a timescale much longer than the orbital timescale. But basically, this is using a classic asymptotic technique. The disk is thin, so we introduce scaled coordinates to resolve the internal structure of the disk and to capture its evolution on timescale much longer than the orbital motion. And then the equations of fluid dynamics are expanded in powers of a small parameter, which is essentially the aspect ratio of the disk, which is also a measure of the sound speed relative to the orbital speed. And broadly speaking, what you get out of this, at the 0th order in this expansion, you just recover the orbital motion as you would for test particles. So that's consistent with the assumption of a Keplerian orbit as the leading approximation to the motion. At the next order in this small parameter, we find that there is an oscillatory internal flow within the disk. And this is driven by the geometry of these non-standard disks. I'll say a bit more about that in a moment. And then at the next order, there is a mean flow, which includes the accretion flow that you would have in a standard disk carrying mass through the disk, causing it to evolve, and indeed a slow evolution of both the shape of the disk and its mass distribution, driven by the various internal stresses, and that's ultimately what we're most interested in. So, okay, this is a very mathematical procedure, but it also has a physical meaning, because this asymptotic analysis, it allows you to separate the different length scales in the problem and the different time scales, and therefore it helps to clarify the physical processes that are going on, and it really helps with the interpretation of the physics. So now regarding this oscillatory internal flow, that is particularly interesting in the case of warped disks. Now in a standard disk, there is a stratification of the pressure in the vertical direction perpendicular to the disk plane. So we have high pressure on the midplane and low pressure away from it. That's basically a hydrostatic balance between the pressure gradient and, well, the small component of the gravity of the central object that's pulling you down towards the midplane. Now, when the disk is warped, that corresponds locally to a misalignment between the midplane of the disk and the local orbital plane. And that introduces some horizontal pressure gradients, which have this sort of arrangement. This is like a cross-section through the disk. And now, from the perspective of the fluid that's orbiting through this structure, it sees these pressure gradients varying at the orbital frequency, which is also the natural frequency of horizontal motions, because the epicyclic frequency, at least if the disk is Keplerian, the epicyclic frequency, which is the natural frequency of horizontal perturbations of an orbit, is equal to the orbital frequency. And that means that a resonance occurs in Keplerian disks, causing these internal flows to be anomalously rapid. And correspondingly, there are large internal torques, and that means that warps evolve especially rapidly in Keplerian disks, which are, of course, the most important ones in astrophysical applications. Now, in eccentric disks, there's another important phenomenon that as the fluid flows around an elliptical orbit, of course, its distance from the central object varies at the orbital frequency, and therefore so does the vertical component of gravity, which is compressing the disk. In addition, if there's an eccentricity gradient or a twist in the disk, then the orbital velocity field in the plane of the disk has a non-zero divergence that oscillates at the orbital frequency as well. So both of these are actually will cause the disk to oscillate vertically, not to be in hydrostatic equilibrium. And so it undergoes a forced breathing oscillation, which can easily become nonlinear. So here, for example, is a calculation of the variation of the scale height of the disk with azimuth around a disk with a constant eccentricity. And we can get into a very extreme vertical oscillation, especially if the disk is isothermal, which means it's very compressible. The scale height can become absurdly small, actually, at pericenter, if the eccentricity is more than about a half. And this sort of thing turns out to be very important for the tidal disruption disks. Now, if you like equations, here are some equations. This is illustrating what some of the equations that can be derived in the case of ideal linear theory. So for an inviscid disk where only pressure is contributing to the evolution, basically. So warp disks can be described in a linear approximation by a pair of equations like this, one for the tilt and another for the internal torque associated with these internal flows. And basically, in the Keplerian case, these combine to produce something like a classical wave equation for the warp, saying that the warp propagates radially through the disk as a result of pressure at a speed that's some fraction of the sound speed in the disk. If you had a significantly non-Keplerian disk, then you would get something more like a Schrödinger equation, a dispersive wave equation. And then in the case of eccentricity, for small eccentricities, we do get something similar to a Schrödinger equation, a dispersive wave equation for the complex eccentricity. And there's a distinctive term here due to the 3D effect, this vertical breathing oscillation that I mentioned. So one application of that actually is to the observed eccentric disks around BE stars, these massive and rapidly rotating stars that expel a circumstellar disk. As I say, the eccentricity equation can be converted into an analogous Schrödinger equation, and the problem of finding an eccentric mode around a BE star is equivalent to looking for a bound state of the Schrödinger equation in an effective potential well. And it turns out that this 3D effect that I mentioned, due to the pressure and the vertical oscillations, produces a deep effective potential well in these disks, which can support a bound state. The interpretation of that is a naturally confined prograde processing eccentric mode close to the star, which is in agreement with observations. Now, more generally, these evolutionary equations are nonlinear, and they can be dispersive wave equations. They also have a diffusive character if dissipative effects such as viscosity, or modeling turbulent stresses really, is included. And it has been found that, well, these evolutionary equations can predict instability, sort of diffusive instability, if, for example, the diffusion coefficient for the warp is a decreasing function of the amplitude of the warp. You can get diffusive instabilities in this type of nonlinear diffusion equation. And that is thought to be related to the onset of the breaking of these warp disks beyond a critical amplitude, and something that deserves further investigation. I mean, what I would say about that is that this effect is seen in basically laminar viscous flows, and also it's most likely to occur in the isothermal disks, which are the ones that have usually been simulated, because in that case there's no thermal feedback between the presence of the warp and the behavior of the disk, so that poses a limitation basically on how much torque it can transfer without breaking. Okay, well, I would like to mention, yes, some of the generalizations of the shearing box model that we've worked on for warped and eccentric disks. The standard shearing box is a classic local representation of an astrophysical disk. We just focus in on a patch of the disk and represent it as a uniform shear flow in a rotating frame of reference. And this model has been widely used for both analytical and computational studies of the local physics of disks, waves, and instabilities, and turbulence, and so on. But it is based on a circular coplanar disk. Now, for a warp disk, made of variably inclined circular orbits, we can do a similar construction. That is, pick out a reference orbit somewhere in this disk and go into a rotating frame that rotates with this orbital motion. And now, from the perspective of this local frame of reference, the geometry of the disk oscillates at the orbital frequency, at least in as much as the shape of the warp disk is fixed in the inertial frame. So as we go around, this box sees this oscillating geometry, which is responsible for forcing these internal flows. And this can be built into the coordinate system, so that we have now an oscillatory vertical shear like this due to the presence of the warp, in addition to the steady orbital shear in the plane of the disk. Something related can be done for eccentric disks by making boxes that move and are deformed according to the orbital motion. And in general, that involves some oscillatory compression here in the horizontal directions. Okay, and we have used this type of computational model to understand the onset of hydrodynamic instability and the production of hydrodynamic turbulence in these flows, it's a novelty because people generally have thought that hydrodynamic turbulence doesn't occur in astrophysical disks, that you need magnetic fields to produce turbulence. So, I mean, roughly speaking, what's happening here is a parametric instability, a parametric resonance, which means that you're taking, and this is the dispersion relation for waves in a disk, frequency versus radial wave number. There are high frequency acoustic waves and low frequency inertial waves restored by the Coriolis force. So here we're finding pairs of inertial waves whose frequency differs by the orbital frequency, and they have the same radial wave number. This pair of waves can be destabilized by coupling to the warp or the oscillatory geometry. And that leads to an instability with a growth rate that can be calculated and increases with the warp amplitude. The unstable modes are basically feeding off the oscillatory shear flows in the disk. So they produce Reynolds stresses that extract energy from that and grow as a result. Well, at least at the time we were doing this work, there was no evidence of this type of instability in any numerical simulations of warp disks. So we set out to do some local computations using this warped shearing box model. This is with Simeon Pardakoper. And here we showed that the instability leads to hydrodynamic turbulence. Now, interestingly, this can occur even if the warp is extremely small, and that's because of this resonance in Keplerian disks, that the magnitude of the internal shear flows can be very significant, even if the warp is very small, so small that it would be unobservable. So we may have hydrodynamic turbulence in astrophysical disks that don't even appear to be warped. So for example, at this sort of amplitude, where is what I could call a 1% warp. Okay, the nonlinear outcome is often a statistically steady, a hydrodynamic turbulence with measurable properties, and it has internal torque coefficients that can be measured, and they're different from those of the laminar disk without the turbulence. And that means that the evolution of the warp and of the disk generally will be different when it enters this turbulent state. But there are some quite complicated issues here to do with hysteresis and the nonlinear nature of the transition to the turbulent state. Now, very recently, I've been working with Hongping Deng, who was Lucio's PhD student in Zurich. And he's been doing some very nice global simulations of warp disks, not using the SPH method, but using the meshless finite mass method, which has some superior properties. It's better able to resolve these internal flows and small-scale instabilities. So using some very high resolution simulations here, he was able to find this parametric instability and turbulent motion occurring in global simulations of warp disks for the first time. The signature of this, by the way, are these sort of oblique, this is showing the breaking nonlinear inertial waves. Internal waves tend to break when they exceed a critical amplitude, and that's what's happening here. Now, it's also possible to study some aspects of warp disks actually using a standard shearing box, which means you don't have to recode the fluid dynamical equations in this funny coordinate system. So that has a number of advantages. So roughly speaking, the idea is to think of, well, perhaps a larger shearing box. And now, okay, we've got this warp disk. Here I'm sort of plotting the radial cross-section of a warp disk at various orbital phases as this box goes around the reference orbit. Now, to the extent that the warp is stationary in the inertial frame, what's happening in this local frame is just that each piece of the disk is oscillating up and down at the orbital frequency, which is a free motion of test particles. Any evolution of the warp on a longer timescale would correspond to a modulation of this vertical oscillation. So that's what we should be trying to detect. So as a proof of concept, here's a simulation of a very simple setup of a gas disk with this sort of corrugation representing a warp. And okay, you basically see each fluid element oscillating up and down at the orbital frequency. But of more interest is what happens on a longer timescale of many orbits. And we'll see that after some time, instability occurs. It's in this case, the parameters are right for this parametric instability to occur. Inertial waves are amplified and they break and they produce this turbulent motion. Now, if we view the same simulation stroboscopically, that's once per orbit, then we can filter out that vertical oscillation and focus on what's really the true evolution of the warp in this system. And there you see, well, the warp propagates. That's the propagation of the bending wave due to pressure. But you also see in this case, it's damped out by the turbulence that results from this instability. Finally, I just wanted to mention this affine model that I worked out, which I think has potential to address some of these situations. It doesn't address the small-scale instability, but it could be useful for long-term simulations in which that doesn't occur. And this is motivated by the fact that for decades people have used two-dimensional fluid equations to represent thin disks. That is, ignoring completely the vertical dimension perpendicular to the disk plane. And that's actually very difficult to justify. So the idea here is to restore certain degrees of freedom. So rather than thinking of the disk as made of fluid elements that can only move in a plane, we think of them as fluid columns that have some vertical extension, and their translations can take them out of the disk plane to describe situations like a warped disk. But they can also undergo expansions and contractions parallel to their length, and they can undergo rotations or tilts, because that is exactly the sort of shearing motion that's happening inside these warped and eccentric disks. So this turns out to have just the right degrees of freedom to describe the large-scale properties of these systems. And you can write down, well, with a sort of minimal approximation, you can write down a Lagrangian for this system and then derive the evolutionary equations from that, which then inherits the right sort of conservation properties. So far, that's only been done for ideal fluids, but it does promisingly reproduce basically everything we know so far about warped and eccentric disks in terms of the global asymptotic theories. Okay, and just an example of what that can produce. When that's combined with the local model, we can, for example, compute nonlinear traveling bending waves, which is a way of understanding the physics of warp propagation in a nonlinear regime. And that one thing that's led to really is a clarification of what the essential nonlinearity in that problem is. It turns out to involve the coupling of these three oscillators. The vertical oscillator, in which the entire disk is just going up and down, that corresponds to the inclination of the orbits. There's this horizontal shearing oscillator, which is the internal flow excited by the oscillatory geometry in the warp disk. And then this breathing motion, which is coupled nonlinearly in the case of warp disks. And it turns out to be the nonlinear coupling between these three oscillators that's the key to understanding the nonlinearity, and indeed that we believe is related to the breaking process for the warp disks. Okay, so I see that my time is essentially up. So just to summarize, Keplerian disks are commonly warped or eccentric as a result of companions, misalignments, and instabilities. Eccentricity and inclination propagate through the disk by means of pressure and self-gravity, and they're damped by various dissipative processes. We've seen that warps evolve especially rapidly in Keplerian disks because of this important resonance. There are a couple of instability processes that deserve further study, a large-scale instability that leads to the breaking of warp disks, and a small-scale instability that produces turbulent motion. And from the theoretical and computational point of view, we've seen that local models can be very effective. The shearing box model can be generalized to study these situations, and that's useful for focusing on the small-scale physics. So I'll stop there, and I'm happy to take any questions.
Yeah, so thank you, Gordon. Thank you very much for Gordon to give us a very interesting talk. So now we'll move on to the question sections. If you have any questions, you can feel free to raise your hand or comment on chat. So I already see a couple of hands here. So maybe I have Andrea to ask the first question. Andrea, please.
Yeah, thanks for the nice talk. I just have a quick question about the hydrodynamic instability. I guess I'm wondering if your disk is ionized, so it also experiences magnetorotational instability, do you expect these two sources of turbulence to amplify each other? Or is there some sort of regulation that could happen?
That's a very interesting question. And I think, yeah, the competition and interplay between these two quite different instabilities would be very interesting to look at. It may be that, let's say, if the eccentricity or inclination is sufficiently small, then the MRI dominates. But in other situations, the hydrodynamics takes over. It's a little hard to anticipate how they might interact, but I do think that's a very interesting problem to look at.
Cool, thank you.
Lucio, next, you can ask questions.
Yeah, so thanks for the great talk first. And I was very interested in your last part on the affine model. I was wondering, do you think it's possible with some further work, of course, to include in some form the effect of cell gravity, describe the effect of cell gravity actually in your affine model? Because even in the case of the cell gravitating disks, I think a major limitation in our understanding has always been that you do the linear perturbation theory, assuming again a thin disk, and so you don't have any three-dimensional structure there. And then the next step is you do numerical simulations to do the full 3D disk in the nonlinear stage. But there's no approach in between that would be helpful actually to understand better the transition to the nonlinear regime in a three-dimensional disk.
Yes, so that's again a very interesting question, and I have become quite interested recently in the three-dimensionality of the gravitational instability for another application. But I'm currently working with a PhD student, Callum Fairbairn, who's working on, well, let's say a particular version of this affine model, and he has made good progress on incorporating self-gravity into that version. So it's not, let's say, it's not ready yet, but I think, although it's not possible to do it in an exact way, I mean, it does involve a somewhat ad hoc approximation, but I think with some modeling, there is a reasonable way to do this. And the fact that the equations of motion can be derived from a Lagrangian basically means that you just need to model the self-gravitational energy term, and then everything else follows from there.
Oh, that's very interesting. Yeah, looking forward.
So, Jerome, you want to ask a question?
Yep. Hi, Gordon. Very nice talk. Thank you very much. It was great. I have a question regarding the possibility to estimate the energy or the power dissipated by this instability using somehow the work that you've done with Barker to ultimately get to an observable that could allow to test those models.
Yes, well, that's I haven't thought that far, I have to admit. But I suppose then you would want to, when you talk about an observable, you would be referring to the enhanced luminosity, perhaps, of a warped or eccentric disk as a result of this instability. I think that's an intriguing possibility, and as we develop models with better thermal physics, because frankly the thermal physics content of these models has been quite primitive so far, often dealing with isothermal or adiabatic fluids. But when the viscous dissipation or turbulent dissipation and radiative cooling are taken into account, that allows the possibility to predict, let's say, the non-axisymmetric emission from these situations, which has some possible observational consequences. But maybe you were thinking of a more theoretical way to estimate this energy dissipation.
Yeah. Thank you.
So next, Wilhelm, you want to ask a question?
Yeah, thank you, Gordon, very much for this wonderful talk. I have a question concerning this generation of turbulence from a slightly warped disk. I mean, it seemed to me that when the simulations were continuing, that the warps disappear slowly. So doesn't the turbulence work then against the initial state that you have, or how is the long-term evolution of that process?
Well, that's a very good point. And of course, if you just had a freely decaying warp, then the fact that the warp produces turbulence that accelerates the decay of the warp would indeed tend to produce a self-defeating process here. So I guess we would have to rely here on the idea that the warp is forced by some misalignment in the system, which cannot go away on a short timescale. So, and indeed, there are many astronomical situations where that's the case, that there is a misalignment and there's a sufficient amount of angular momentum in the components that are misaligned that it would take a very long time to remove that misalignment by dissipation. So in that case, we could expect some persistent turbulence. But even there, the fact that the turbulence enhances the dissipation of the warp would mean that the alignment timescale for the system would be accelerated.
Yeah, many thanks. Yeah.
Okay, so if there's no other extra questions, we thank you, Gordon, again. And we wish in the future we can have a chance to invite you in person to Zurich again to have a detailed discussion with you on all of your research on astrophysical disks. So yeah, thank you very much. And yeah, today our seminar will end here. And thank you for everyone who participated in this seminar.
Thank you all very much.
Thank you.
Yeah.